Welcome back to the Coding Cove. If you're new here, make sure to subscribe and turn on notifications so you never miss another C programming tutorial. Today, we're learning one of the most important skills in C programming: how to safely delete nodes from a singly linked list. Now, deleting a node might sound simple. Just remove it from the list and move on, right? Not quite. In C, deleting a node is one of those operations where a single mistake can cause memory leaks, dangling pointers, or even crash your entire program with a segmentation fault. The good news is that once you understand the logic behind the process, deleting nodes becomes much easier than it first appears. In this video, we're going to build that understanding step by step. We'll start by learning what deletion actually means in C. Then we'll delete the first node in a linked list. Later in the video, we'll move on to deleting the last node and deleting a node by a specific value. Finally, we'll look at the most common mistakes programmers make and how to avoid them. So let's get started. Before we write a single line of code, we first need to understand what it actually means to delete a node. Unlike languages such as Python or Java, C does not automatically clean up memory for you. There is no garbage collector running in the background. Instead, you are responsible for every piece of memory that your program allocates. Because of that, deleting a node always involves two separate steps. The first step is to remove the node from the linked list. In other words, we reconnect the surrounding nodes so the node we want is no longer part of the chain. But here's the important part. Removing the node from the list does not remove it from memory. The memory is still sitting there, even though nothing in our program can reach it anymore. That's why we need the second step. We must explicitly return that memory back to the operating system. Only after completing both of these steps is the node truly deleted. Think about removing a book from a bookshelf. Taking the book off the shelf doesn't mean you've thrown it away. It's still sitting on your desk, taking up space. To completely get rid of it, you also have to remove it from the room. Deleting a linked list node works exactly the same way. First, remove it from the structure. Then release the memory. Never stop after the first step. Let's look at why this matters so much. Imagine we have a linked list containing 3 nodes. 10 points to 20. 20 points to 30. Now suppose we want to delete the node containing 20. We reconnect the first node directly to the third node. Logically, everything looks perfect. The list still works exactly as expected. But what happened to the node containing 20? If we forgot to release its memory, that memory is still allocated. Our program has completely lost access to it. Nothing can use it anymore. Nothing can free it later. That memory is permanently wasted until the program finishes running. This problem is called a memory leak. One memory leak may not seem like a big deal. But imagine a server deleting thousands of nodes every minute. Every forgotten piece of memory continues to accumulate. Eventually, the program consumes more and more memory until performance suffers, or even worse, the application crashes. That's why experienced C programmers follow a simple rule. Every piece of memory that gets allocated should eventually be released. If you remember only one lesson from today's video, let it be this. Whenever you remove a node from a linked list, always make sure you release its memory afterwards. Now that we understand the 2 rules of deletion, let's look at the 3 different ways we can remove nodes from a singly linked list. The first method is deleting the first node. This is the simplest and fastest deletion because the node we want is already at the front of the list. The second method is deleting the last node. This one is slightly more difficult because we have to travel through the list before we can reach the end. Finally, we have deleting a node by a specific value. This is the most flexible method, but it's also the most challenging because we first have to search for the node before removing it safely. Although these 3 algorithms are different, they all follow the exact same principle. Reconnect the list first. Release the memory second. That order never changes. Let's begin with the easiest deletion of all. Deleting the first node. Suppose our linked list contains the values 10, 20, and 30. The head pointer is currently pointing to the node containing 10. Our goal is to remove that first node safely. The very first thing we should always do is check whether the list is empty. If there are no nodes, then there's nothing to delete. This simple check prevents our program from trying to access memory that doesn't exist. Once we know the list isn't empty, the next step is extremely important. Before moving the head pointer, we first save the address of the current first node inside a temporary pointer. This temporary pointer acts like a bookmark. It remembers exactly where the first node is. Now we can safely move the head pointer forward so that it points to the second node. At this point, the linked list now begins with 20 instead of 10. Logically, the first node has been removed from the list. However, it still exists in memory. That's why our final step is to release that memory. Once we do that, the node is completely gone. The operating system is now free to reuse that memory whenever it needs to. Some programmers also set the temporary pointer to null immediately afterwards. While this isn't strictly required, it's considered good programming practice because it prevents the pointer from accidentally being used again later. One thing you'll notice about deleting the first node is how efficient it is. We never have to search through the linked list. We don't care whether the list contains 3 nodes, 300 nodes, or 3 million nodes. The process is always exactly the same. We perform the same sequence of operations every single time. That's why deleting from the beginning is considered a constant time operation. It is one of the fastest operations you can perform on a linked list. Unfortunately, that convenience disappears when we try to delete the last node. Unlike the first node, we can't jump directly to the end of a singly linked list. Instead, we'll have to travel through the list one node at a time before we can safely remove the final node. And that's exactly what we'll learn in the next section. Now that we've mastered deleting the first node, it's time to move on to something a little more challenging. Deleting the last node. At first glance, it might seem like deleting the first node and deleting the last node should be equally simple. After all, we're only removing one node. But there's one important limitation we have to remember. A singly linked list only moves in one direction. It only knows how to move forward. There are no backward links. That means we can't simply jump to the last node whenever we want. Instead, we have to travel through the list one node at a time until we reach the end. This extra traversal is what makes deleting the last node more expensive than deleting the first one. Let's imagine we have a linked list containing the values 10, 20, and 30. Our goal is to delete the last node, which contains the value 30. You might think we simply move all the way to the last node and delete it. But if we do that, we run into a problem. Once we're standing on the last node, we no longer have access to the node before it. And that's exactly the node we need. Why? Because before deleting the last node, we must tell the second to last node that it is now the end of the list. In other words, its next pointer must become empty. So instead of stopping at the last node, we deliberately stop one node earlier. That gives us access to both the final node and the pointer that connects them. Once we're there, the process becomes straightforward. We temporarily store the last node. We disconnect it from the list. Then we release its memory. The second to last node now becomes the new end of the linked list. Let's think about how we actually reach that second to last node. We begin at the head of the list and move forward one node at a time. But we don't keep walking until we reach the end. Instead, we stop when the next node is the final node. This allows us to safely disconnect that final node without losing access to it. If we accidentally walked all the way to the last node first, we'd have no way to update the previous node's connection. That's why this stopping point is so important. It's a small detail, but it makes the entire algorithm work. Because we have to walk through the list before deleting anything, deleting the last node is slower than deleting the first node. The larger the list becomes, the longer this traversal takes. If your linked list has 5 nodes, you'll only take a few steps. If it has 5 million nodes, you'll have to walk through almost the entire structure. That's why deleting from the end is called a linear time operation. Its running time grows as the size of the list grows. Now let's move on to the most powerful deletion algorithm. Deleting a node by a specific value. This is the algorithm you'll use most often in real applications because you usually don't know where the data is located. Instead, you know what you're looking for. For example, suppose we want to delete the node containing the value 30. Unlike deleting the first or last node, we first have to search the linked list until we find that value. Searching introduces a new challenge. Remember, a singly linked list only moves forward. Once we leave a node behind, we can't go back to it. That means when we finally arrive at the node we want to delete, we also need access to the node immediately before it. Without that previous node, we can't reconnect the list. So instead of using just one pointer while searching, we use two. One pointer represents our current position. The second pointer stays one step behind. As both pointers move through the list together, the previous pointer is always tracking the node directly before the current one. Think of it like hiking through a forest. One person walks in front. Another follows just a few steps behind. Wherever the leader goes, the second person follows. By the time the leader reaches the destination, the second person is perfectly positioned just behind them. Our two pointers work exactly the same way. Let's see what happens when we finally find the value we're searching for. Suppose our previous pointer is pointing to the node containing 20. Our current pointer is pointing to the node containing 30. And 30 points to 40. To remove 30, we simply reconnect 20 directly to 40. The node containing 30 is now completely bypassed. The linked list flows smoothly from 20 to 40, as though 30 was never there. Only after we've safely reconnected the list do we release the memory occupied by the removed node. Notice something important here. We never released the memory first. If we did, we'd lose access to the next node and risk breaking the entire linked list. Always reconnect the pointers before releasing memory. That order is absolutely essential. Searching also introduces another possibility. What if the value isn't actually in the linked list? Imagine searching for the value 100, but every node has already been checked and the value never appears. Instead of crashing or producing unpredictable behavior, a well-written program simply reports that the value was not found. It then exits the deletion function without changing the linked list. Handling situations like this is called handling edge cases, and it's one of the biggest differences between beginner code and professional code. Good programs don't just work when everything goes perfectly. They also behave correctly when something unexpected happens. There are a few other edge cases we should think about as well. What if the list is empty? What if there's only one node? What if the value we're deleting happens to be the first node? Each of these situations requires slightly different handling. That's why you'll often see these checks near the beginning of a deletion function. Although they might seem repetitive, they prevent many of the crashes beginners experience while learning linked lists. Let's quickly compare the three deletion algorithms we've learned so far. Deleting the first node is the fastest because no searching is required. Deleting the last node is slower because we must travel all the way to the end of the list. Deleting by value is also a linear time operation because we may have to search through every node before finding the one we're looking for. Even though these algorithms have different levels of complexity, they all follow the exact same pattern. Find the node. Reconnect the list. Release the memory. Every successful deletion follows these same three steps. Now that we've learned all three deletion algorithms individually, it's time to put everything together and see them working inside one complete program. Understanding an algorithm is important, but watching it work from beginning to end is what really builds confidence. To test our deletion functions, we first need a linked list to work with. So before we delete anything, we create a few sample nodes and connect them together to build our list. Once our linked list has been created, we can begin testing each deletion function one at a time. We'll start by deleting the first node. After running the function, we print the linked list. The first value is gone, and every remaining node is still connected correctly. That's exactly what we expected. Next, we test deleting the last node. Again, we print the linked list. This time, the final node has disappeared, and the second to last node has become the new end of the list. Everything still works perfectly. Now it's time for the most flexible deletion method. Deleting by a specific value. We choose a value somewhere in the middle of the linked list and run our deletion function. Once again, we print the updated list. The target node has been removed, while the remaining nodes stay connected in the correct order. Finally, let's test something that every good program should be prepared for. What happens if we try to delete a value that doesn't exist? Suppose we search for a value like 100. Our program carefully searches through the entire linked list. When it reaches the end without finding that value, it doesn't crash. It doesn't modify the list. Instead, it simply reports that the value was not found. The linked list remains exactly as it was before. This is an important reminder that good programs don't just handle success. They also handle failure gracefully. Once we've finished testing every deletion function, there's one final cleanup step. Even though our program is about to finish running, we should still release every remaining node in the linked list. Many programmers create a helper function specifically for this purpose. Its job is simple. Starting from the head of the list, it repeatedly deletes nodes until the linked list becomes completely empty. This ensures that every block of dynamically allocated memory is returned to the operating system before the program ends. Developing this habit early will make your programs safer, cleaner, and much easier to maintain as they grow larger. Now let's talk about the mistakes that cause the majority of bugs when working with linked lists. The first, and probably the most common, is forgetting to release memory. Imagine removing a node from the linked list but never returning its memory. Your program continues running normally. Everything appears to work. But hidden beneath the surface, memory is slowly disappearing. Every forgotten node leaves behind another memory leak. Over time, these leaks accumulate. The longer the program runs, the more memory it wastes. This is one of the biggest reasons long-running applications eventually slow down, or even crash. The solution is simple. Every time you remove a dynamically allocated node, make sure you release its memory. The second mistake is even more dangerous. This is called a dangling pointer. A dangling pointer happens when you release a node's memory but continue trying to use that same node afterward. Remember, once memory has been released, it no longer belongs to your program. Trying to read from it or write to it is unpredictable. Sometimes your program may appear to work. Other times it may crash immediately. And occasionally it may produce strange bugs that are incredibly difficult to track down. That's why experienced programmers follow another simple rule. Once you've released a pointer, never use it again. Many developers even set that pointer to null immediately afterward. Doing so makes it obvious that the pointer no longer references valid memory and helps prevent accidental reuse. Another common mistake is forgetting to check whether the linked list is empty before attempting a deletion. Imagine trying to remove a node from a list that doesn't contain any nodes at all. If your program immediately starts accessing data that isn't there, it will almost certainly crash. That's why every deletion function should begin by asking one simple question. Does the linked list actually exist? If the answer is no, the function simply returns without doing anything. Sometimes the safest operation is doing nothing at all. There's another mistake that often appears when deleting the last node. Remember that we need to stop at the second to last node. If our traversal goes one step too far and lands on the final node instead, we've already lost access to the node we needed to update. Without that previous connection, we can't safely disconnect the last node. A tiny mistake in the traversal logic can completely break the algorithm. This is why careful pointer movement is so important when working with linked lists. Now let's compare the efficiency of the three deletion algorithms. Deleting the first node is the fastest operation. Since the head already points directly to the node we want, no searching is required. The amount of work stays exactly the same regardless of whether the list contains 5 nodes or 5 million. Deleting the last node takes longer because we must travel through the linked list before reaching the end. The larger the list becomes, the longer that traversal takes. Deleting by a specific value behaves the same way. In the worst case, we may have to examine every single node before finding the one we're looking for, or before determining that it doesn't exist at all. Understanding these performance differences helps you choose the right algorithm depending on the situation. Sometimes the fastest solution isn't just about writing less code. It's about selecting the right approach for the data structure you're using. Before we finish, let's summarize the 4 rules you should always remember whenever you're deleting nodes from a singly linked list. First, always check whether the linked list is empty before attempting any deletion. Second, always keep a reference to the node you're about to remove before changing any pointers. Third, once the node has been safely disconnected from the linked list, immediately release its memory. And finally, if your deletion changes the beginning of the list, make sure the updated head pointer is returned so the rest of your program knows where the linked list now starts. If you follow these 4 rules every single time, you'll avoid the majority of bugs programmers encounter when working with linked lists. Today we've learned that deleting a node is much more than simply removing data. It's about managing memory responsibly. You've learned how to delete the first node. You've learned how to delete the last node. You've learned how to delete a node by a specific value. You've also learned how to prevent memory leaks, avoid dangling pointers, handle edge cases, and understand the performance of each deletion algorithm. Mastering these concepts is an important milestone in becoming a confident C programmer. Memory management is one of the defining features of the language. The more comfortable you become with pointers and dynamic memory, the more control you'll have over how your programs behave. If you found this video helpful, don't forget to leave a like, subscribe to the Coding Cove, and share this video with someone who's learning data structures in C. Thanks for watching, keep practicing, and I'll see you in the next one.